So far in this course, we have looked at two different kinds of frequency domain representations for signals. If a signal is periodic, we have used a Fourier series representation to represent this signal. And when dealing with non-periodic signals, we have used what is called the Fourier transform to deal with non-periodic signals. Now, in this lecture, I'm going to show that it's possible to define a Fourier transform for periodic signals as well. And the main advantage of doing something like this is that the Fourier transform can then be used to deal with both periodic and non-periodic signals under just one framework. Okay. Now the natural question to ask then is, why did we bother about Fourier series representations of periodic signals? And the answer to that is, even though we're going to derive the Fourier transform of periodic signals in this lecture, the Fourier series representation of such signals plays a crucial role in deriving the Fourier transform. Okay. Now, to derive the Fourier transform of periodic signals, let's recall with a few basic Fourier transform pairs. Now, the Dirac delta function delta of t has a Fourier transform which is just 1. And you may also recall that the Fourier transform of the signal, which is 1 for all values of t, is 2 pi times delta of omega. And another important result to recall is that the signal e to the j omega naught t has a Fourier transform which is 2 pi times delta of omega minus omega naught. Okay. Now this is perhaps the most important result. Now this can be derived in one of two ways. Either we can start with this result and then use the fact that multiplication in time by a complex exponential corresponds to a shift in frequency. Or another thing to do is to directly start with this expression here and plug this into the inverse Fourier transform formula and then use the shifting property of the delta function to see that in fact you end up with the inverse Fourier transform, which is e to the j omega naught t. Okay. Now, if this is not obvious to you, I would suggest that you stop the video here and try the second approach that I just mentioned and convince yourself that these two form a Fourier transform pair. Okay. In the same way, you can start with the Fourier transform relation and you can show that the Fourier transform of delta of t minus t is e to the negative j omega times t. Okay. Okay. So now that we are armed with this, let us say that we have a periodic signal x of t. Let x of t be a periodic signal with a time period of capital T. Okay. Time period capital T and fundamental frequency 2 pi over t. Now, we know that we can write a Fourier series representation for x of t. Namely, we can write x of t as the sum of weighted complex exponentials, or x of k times e to the j k omega naught t for k going from negative infinity to positive infinity. That's just the Fourier series representation for x of t. Okay. Now, the way we are going to derive the Fourier transform of x of t is to apply the Fourier transform to both sides of this expression that we have. So if I take the Fourier transform of x of t, namely we get x of j omega. Now the Fourier transform must be the Fourier transform of this signal, right? And using this relationship, we can see that the Fourier transform of this is summation x of k times 2 pi times delta of omega minus omega naught. Or equivalently, this is 2 pi times summation k running from negative infinity to positive infinity x of k delta of omega, oh oops, I'm sorry, this should be k omega naught, delta of omega minus k omega naught. And indeed this is the main result. So let's think a little bit about what this result means. Basically what this result says is the following. If x of t is periodic with a time period t and therefore a fundamental frequency of omega naught, which is 2 pi over t, what this basically says is that the Fourier transform of x of t simply consists of a bunch of impulses. And how do we see that? Well, we see that from this expression here. This expression says that x of j omega is 2 pi times summation x of k delta of omega minus k omega naught, which essentially means all you have are impulses at integer multiples of omega naught, right? Now the strength of these impulses at each of these locations is given by 2 pi times the Fourier series coefficient x of 0, x of 1, so on and so forth. So this one will be 2 pi times x of 3, this is 2 pi times x of negative 2, so on and so forth. Okay, and this is kind of the picture that you want to keep in mind. The picture that you want to keep in mind is that the Fourier transform of a periodic signal consists of a bunch of impulses, or infinitely many impulses. The impulses all occur at integer multiples of omega naught, and the strength of these impulses are 2 pi times the Fourier series coefficients. Okay, now let me work out a couple of examples. So let's look at the signal x of t is cosine omega naught t. Now the question is, what is the Fourier transform of x of t? Well, clearly x of t is periodic and the fundamental frequency is omega naught, right? The time period is going to be 2 pi over omega naught and the fundamental frequency is omega naught. So to find the Fourier transform of x of t, we'll have to find the Fourier series coefficients. And how do we find the Fourier series coefficients? Well, I would urge you to stop the video here and think about this for a minute. If you have thought about it and you still need help, well, the way we find this is the easy way to find this would be to use what we call as the method of inspections, or method of inspection rather, which would be to use Euler's formula to write cosine omega naught t as half of e raised to j omega naught t plus half of e raised to negative j omega naught t, and from here we can simply read off the Fourier series coefficients. Now the first term corresponds to k equal to 1, so this means that x of 1 is 1/2. The second term corresponds to k being negative 1, so this tells us that x of negative 1 is also a half. Therefore x of k is half if k is equal to 1 or k equal to negative 1, and it's 0 otherwise. Okay. Now these are the Fourier series coefficients. Excuse me. Now how do we get the Fourier transform from here? Well, to get the Fourier transform, what do? We realize that the Fourier transform has impulses, and in this case, since only two of the Fourier series coefficients are non-zeros or non-zero, you get two impulses, one at omega naught, and the strength of this impulse is 2 pi times x of 1, which gives us pi, and the strength of the impulse at negative omega naught is also pi, and therefore, so this picture here shows the Fourier transform of x of cosine omega naught t. Now mathematically we can write this as pi times delta of omega minus omega naught plus pi times delta of omega plus omega naught. Now this delta corresponds to this, and this delta corresponds to this. Now in exactly the same way, we can derive the Fourier transform of x of t is equal to sine omega naught t. And the way we can find the Fourier series coefficients of sine omega naught t is again to use the method of inspection, which is to write sine omega naught t as e raised to j omega naught t minus e raised to negative j omega naught t divided by 2j. And this basically tells us that x of 1 is 1 over 2j, x of negative 1 is negative 1 over 2j. And therefore, x of j omega will be pi over j times delta of omega minus omega naught minus pi over j times delta of omega plus omega naught. Now if we were to sketch this, it's normal for textbooks to sketch this function like this. Now what you do have to realize is that pi over j and negative pi over j are imaginary numbers. Nevertheless, just as a schematic, it's kind of common for textbooks to sketch x of j omega like this. Okay. Now the last example I want to show is an example that we use often in when dealing with things like sampling, which is to derive the Fourier transform of a train of impulses. Suppose we consider the periodic signal given by summation over all n, delta of t minus n times ts, where ts is a constant. Okay. Now, if we were to sketch this signal, the signal is a train of impulses. So basically we have, maybe I can you can see that the signal is periodic, right? So the question is, what is the Fourier transform of this signal? Well, we'll do exactly what we did in the last two cases, which is to find the Fourier series coefficients first, and then find the Fourier transform from that. Okay. Now notice that the time period of the signal is t sub s, or equivalently the fundamental frequency is 2 pi over t sub s, and we can call this as omega naught. Okay. Now how do we find the Fourier series coefficients? Well, we can take any one time period of this signal. In this case, it seems easy to choose this one time period that goes between negative ts over 2 and positive ts over 2. And then the Fourier series coefficients x of k are given by 1 over the time period, integral negative ts over 2 to positive ts over 2. And one period of this signal is simply given by delta of t, right, times e to the j k omega naught t dt. If we use the shifting property of the delta function, now this integral is simply this function evaluated at t equal to 0. Right? And so the whole integral simplifies to 1 over t sub s times 1, or equivalently just 1 over t sub s. Well, basically what this excuse me. Basically what this means is that the Fourier series coefficients, all of them have the same value 1 over t sub s. Now that we have the Fourier series coefficients, we can plug this into the formula for the Fourier transform, which is given by 2 pi times the summation over k of x of k times delta of omega minus k omega naught. And we just determined that x of k was 1 over t sub s. Therefore, for x of j omega, we get 2 pi over t sub s times summation k going from negative infinity to positive infinity, delta of omega minus k times 2 pi over ts. And indeed, this is the Fourier transform of the train of impulses. Now, if we were to plot this Fourier transform, notice that this is also a train of impulses in the frequency domain. If I were to plot x of j omega versus omega, now what I get is I get a train of impulses. The important thing to note is that the spacing between the impulses is given by 2 pi over t sub s, and the strength of these impulses is also 2 pi over t sub s. They're all of the same strength. Okay. Now this is an important result to remember. Particularly we will use this in sampling.